Rummy, let's give all the static students a high five. Part 1 ended with this impossible situation, 6 unknowns and 3 equations. However, if we do a preliminary analysis of finding the reactions that support D and E, we can overcome this impossible situation. And that is to find my reaction forces at E and D by analyzing the entire truss. However, had I analyzed the entire truss and found the reaction forces at D and E, meaning dx, dy, ex, then this free body diagram has the external forces that are 1,000 newtons, dx, dy, and ex. That leaves us with 3 unknowns, in which we can solve using some of the forces in the x is equal to 0, some of the forces in the y equal to 0, and some of the moment about a point is equal to 0. So we have 3 equations and 3 unknowns. We should be able to solve this. So we do this first, determine dx, dy, ex. Now we go and analyze the section portion of it, and we no longer have 6 unknowns because we would have found dx, dy, and ex. Therefore, we end up with 1, 2, 3 unknowns, providing us a situation where we can apply the equations of equilibrium, where we have 3 equations. Therefore, 3 equations and 3 unknowns, we can solve it. What I'm trying to demonstrate to you is that that's a lot of work. You don't want to take that approach. The simplest approach is to analyze the left half of this truss, providing a very straightforward computation where we take this free body diagram, take the sum of the forces in the x, some of the forces in the y, and some of the moment about a point equal to 0. So we'll have 3 equations and 3 unknowns, providing us a situation where we can find that force that we want required by the problem statement. So let's do this problem, and I'm going to work it out, and it's going to be a little longer because I want to explain to you some very important approaches to analyzing these trusses. So in this particular problem, we're given several loads that are applied to the truss. There were supports at A and C, and the problem statement already calculated those reactions for us. So they are 4,000 and 2,000 newtons. The problem statement requires that we find the force in member EB, which is right here. So we're interested in the force in this member. They would also like to know whether it's in tension or compression. Solution. So we're going to solve this problem using the method of sections. Method of sections. And I'm going to throw in a method of joints as well, because you can mix both of these approaches in analyzing trusses. Okay, so since we're interested in the force in member ED, when we do the method of section, we have to make sure that we actually cut through or section through that member. So one potential section would be that. So let's see what happens. So if I section the truss at AA, so this is what the free body diagram would look like. So if I were to draw my point E here, my point A, and my point B, then rest of the members would look something like this, where since I've sectioned it, I only draw a portion of member AB as well as a portion of member FB, and EB as well. Let's fix that. And I also have to draw the section of member ED. And D would be somewhere right here. Let me shorten this. Okay. So now what I have to do is draw the externally applied forces. That'll be 1,000 newtons, 3,000 newtons, and 1,000 newtons, along with the reaction force at A. There'll be 4,000. And I am going to assume that member AB is in tension. So I'm going to draw a force like that. And I'm exposing the internal forces. And since it's sectioned, they now become external forces in this particular free body diagram. I'm going to assume that member EB is in compression. So force BF, and I'm going to assume that EB is in tension. FEB. And I'm going to assume that member ED is in compression. So, and we know that this is in line. So I just want to clearly indicate that they are all concurrent at point B. At least those three members are. And we can also visualize that point C over here, which would be approximately right here, is right there. And I can identify that as point C. So there's my free body diagram. And what I have is 1, 2, 3, 4 unknowns. I have 4 unknowns. So I could use my 3 equations of equilibrium, but that still leaves me with 1 unknown. And it seems like an impossible task. And with this free body diagram alone by itself to solve this problem, it is. So how do we overcome this? If we can draw another free body diagram, we have a way out. So let's see what happens if we select another free body diagram and how our analysis changes. So I'm still interested in this member. I want to know the force in member EB. So I'm going to section it right there. I'll call that section BB. And I'm going to draw a free body diagram of this sectioned portion. So I'll do that right here. So I have point E, and this is my section. This is point F right there, and that's my member. And I'll have this portion right here. That's shown right here. I've enlarged it. And I'll have member EB right there. So this line BB is somewhere like along there. So because I've sectioned it, I have now exposed forces in each of these members. So I guess this would be point B, and I guess point D would be somewhere there. So since I've sectioned them, I have to expose the internal forces and make them external forces. So I'm going to assume that member EF is in compression. I'm going to say that member EB is in tension, exactly the same way that I have assumed it up here. I have to be consistent. FEB. And same thing with ED. I have to follow this convention where I said that I'm assuming section ED to be in compression. FDE. And I have to apply that 1,000 Newton force. Okay, so now what we have are two free body diagrams. In the second free body diagram, I have three unknowns, and I have three equations of equilibrium. So let's see where that gets us. So we'll call this FBD number 1. We'll call this FBD number 2. And let's solve this problem. Let's take a look at the two free body diagrams that we have. And instead of jumping into applying the three equations of equilibrium for each of these free body diagrams, let's analyze this for a moment. As you can see, I drew points B, C, and D even when they weren't part of the sectioned truss. So we sectioned it at A. What I'm showing here is to the left of line AA, but I do show points B, C, and D. That's because when you apply the three equations of equilibrium, especially the moment equation, I can take the moment about these points, even if they're not included in this sectioned portion of the truss. So with that said, I note that force FAB, BF, and EB are all concurrent about point B. If I were to take the moment of all these forces about point B, I'm only left with one force, FDE. So applying the sum of the moment about point B for FBD number 1, I can find FDE. Now, if I know FDE, then I can use my free body number 2, and once we know FDE, let's jump to free body diagram number 2 to see what we get. If I take the moment about point E, it's trivial. All the forces are concurrent there. I get nothing. So it's just 0 equal to 0. So next, I can take the sum of the forces in the x is equal to 0. And using this coordinate system, xy, that would lead me to one equation. I'll have sum of the forces in the y. That'll lead me to another equation. And that means I have two equations with two unknowns because we just found FDE using the previous free body diagram. So let's see how that all works out. Let's do that. So FBD number 1, we take sum of the moment about point B is equal to 0. We note that the distance from B to C is 4 meters per the problem statement. And since forces are transmissible, I can move this force to point C, or joint C. That's FDE. And I can express the x component that way and the y component that way. So this would be FDEY, FDEX. According to the problem statement, this is 30 degrees. So here we go. 4,000. This is 4 meters. Right here, that was 2 meters. So I would have the moment arm 4 meters times 4,000. So that's 4 meters times 4,000. And that'll be a negative moment. 4 meters, that would be the moment arm, times 1,000. That would give me a positive moment. 2 meter moment arm times 3,000. This should be 3,000. That would give me a positive moment of 2 times 3,000. This force is in line with point B, therefore no moment is generated. Same goes for this force. FDEX is in line with point B, therefore no moment due to that force. We do have a moment due to the y component. So the moment arm is 4 meters times FDEY, and that would be a positive moment of 4 times FDE in the y component is equal to 0. So we know FDEY is just FDE times sine of 30 degrees. So we'll make that substitution in here, and it'll become minus 16,000 plus 4,000 plus 6,000 plus 4 FDE times sine of 30 degrees is equal to 0. So if we do that, FDE turns out to be 3,000 newtons. As we had previously stated, we're going to take this value, right? So we just found FDE. We're going to take that value and use it in the analysis of free body diagram number 2. So let's see what that looks like. So let's not forget, we're trying to find what the force is in member EB. So we'll do sum of the forces in the y is 0, and we will get the following. And again, just some geometries. This is actually 30 degrees, 30 degrees. So sum of the forces in the y would yield the x component. Sum of the forces in the y would yield the y component of this plus this force plus the y component of that plus this 1,000 Newton going in the negative y direction. So we have, for this one, we have that the y component is going upward, and that would be 30 degrees right there. So it would be FFE sine of 30 degrees. Same thing for FDE. We would have FDE sine of 30 degrees minus FEB minus that 1,000 force, 1,000 Newton force. So in the previous calculation, we found that FDE was equal to 3,000 newtons. So we should take note of that. Now we do sum of the forces in the x is equal to 0. These two forces will have x component, and it would have a value of FFE times cosine of 30, and then FDE times cosine of 30, and that'd be in the negative direction. And we find that using this equation, FFE is equal to FDE, which is equal to 3,000 newtons. So now we can go back to this equation and substitute that in there, giving us values for these two and allowing us to find force EB. So we have 3,000 times sine of 30 plus 3,000 sine of 30 minus FEB minus 1,000 is equal to 0. So we have one unknown, one equation. We solve for that. We get that FEB is equal to 2,000 Newton. Answer turns out to be a positive value. This means that our assumption of FEB going down, or our assumption of member EB being in tension, was correct. Therefore, FEB is in tension, and that's our answer.